Okay, so what we're going to talk about this week are, well, today and part of tomorrow are aldehydes and ketones, some of their reactions. So remember that the functional groups known as aldehydes and ketones, they're characterized by that carbonyl, and that's really what we're going to spend our time talking about for the final 2 weeks of the semester, are compounds that are centered around that carbonyl functional group. Okay, and the difference between aldehyde is that on one side of the carbon is a hydrogen, but with a ketone, you've got carbon-containing groups on both sides of that carbonyl. That's the difference between the two. Okay, so let's talk a little bit about naming. So aldehydes are named, same scheme we've been using. We just change the suffix. Get the parent alkane, and drop the E at the end, and in this case, we're going to put an AL on the end for a suffix. Right? One thing to remember is that in this case, the parent chain must contain that aldehyde group. That carbonyl connected to a hydrogen must be in there. And that actually becomes the first carbon. So there's not much debate regarding the numbering scheme when you have aldehydes. You know which carbon starts the numbering scheme. It's the carbon that's part of the carbonyl and has that aldehyde hydrogen attached to it. Okay. Now, if there is a cyclic compound, then the one interesting thing about aldehydes is that you name the ring and then you use carbaldehyde as the substituent name. So there's really not more than one substituent name when you're dealing with aldehydes. If you're going to name the aldehyde as a substituent, it is always carbaldehyde. And you'll see that in your notes there in some examples. But also this table, which is not in your handout, just points out that there are actually several commonly used names for aldehydes that aren't the same as the IUPAC names. So just be aware of those. Formaldehyde and acetaldehyde and then benzaldehyde are the most common ones. Okay, but you can see down here at the bottom what we commonly call benzaldehyde, according to the IUPAC name, would be benzene, because that's the ring, and then the aldehyde is a substituent, so it would be benzene carbaldehyde. Okay, but the common name, as I said, is just benzaldehyde. Okay, so now let's talk a little bit about naming ketones. So same thing, you drop the E at the end of the alkane parent name, and you replace that with a different suffix. In this case, it's O-N-E, own is how you'd pronounce it. Just like ketone, the name of the compound is going to end with own. And in this case, the parent chain is just the longest one that contains the ketone group. And in this case, you do have to decide which direction you're going to go with the numbers. And it is the one that's nearest to the carbonyl carbon. So numbering begins at the end, nearer to the carbonyl carbon. Okay, so here's some examples. So in this first example here, we've got 6 carbons, 1, 2, 3, 4, 5, 6. Okay, so the parent name is going to be hexane, but we drop the E and put the O-N-E suffix on it. So that's hexanone is how you pronounce that, hexanone. And since the ketone is at position 3, based on this numbering scheme, remember we went to the one that's closest. In this case, it doesn't really matter because it's 3 either direction you go. But it's 3-hexanone. And remember that there is this new way of naming, but it hasn't really caught on yet. So I won't even give you examples in quizzes and so forth with this new naming. Or actually, it's an annotation scheme. It's not so much a naming scheme, but just where to put the numbers. It's not used that much in publications and whatnot. So 3-hexanone is what you'd call this first example. Now over here, notice that we have another functional group in there. There's an alkene. There's that double bond between carbons 4 and 5. Okay, and notice that it does not take priority because we numbered from the carbon that's closest to the carbonyl. So this carbon becomes carbon 1, and then on the second carbon is the carbonyl. Okay, so that we would name this 4-hexene because the double bond is at the position 4-hexene. But then at position 2, we have the carbonyl, so that's 2-O. So 4-hexene-2-O. Okay. So in this case, I think part of the reason why they try to invoke this new naming scheme is to be more consistent. You notice how we had to go into the interior of the compound name to state the position of the ketone functional group. I think the new naming scheme is just to kind of be more consistent due to that. All right, well, you got one over here. Again, you've got multiple ketone functional groups. And so you got the dione because there's 2 of them, and they're at positions 2 and 4. Okay, now something that looks like a ketone, but it's a little different. It's really a kind of a ketone when it's a substituent rather than the parent part of the compound. So if you have that RC double bond O as a substituent, we call that an acyl group, and we talked about this before, particularly when we were talking about Friedel-Crafts reactions, Friedel-Crafts alkylation, Friedel-Crafts acylation. So this is the acyl group. And again, I don't expect a lot from you in naming these. Really, I just want you to recognize the common names. Like I want you to recognize that acetyl is where you have the two carbons. Okay, and one of the carbons is with the double bond oxygens, the carbonyl. Formyl is where you just have the one carbon. Okay, and then there's a hydrogen there. So it's kind of like an aldehyde. But another way of doing that is like formyl. It's a common way of saying it. Okay. And then this one here, benzoyl, because you got the benzene ring, but then you got another carbon that is a carbonyl. The common name for that substituent is benzoyl. Okay. So yeah, I want you to know those three labels just as common names, just like I wanted you to know isobutyl and tert-butyl and isopropyl. Okay, so if there are other functional groups that take priority and we're not going to name the compound based on the ketone functional group, then we will use the oxo prefix to indicate the position of the ketone functional group. So the prefix oxo is used if other functional groups are present and the doubly bonded oxygen is labeled as a substituent on a parent chain. Okay, so for example, this one right here, which is also in your handout, you've got 6 carbons. So we got the parent name of hexane, and we change the suffix to Al because it's an aldehyde. And remember that that identifies also carbon 1. That is your, always with an aldehyde, carbon 1 is the aldehyde carbon. So then at carbon 3 here, I notice that I've got this thing that looks like a ketone functional group. I've got a carbonyl, then I've got a carbon group on one side, and I got a different carbon group on the other side. So that's a ketone. And so the right prefix in this case would be oxo. Okay, so when you want to indicate the position of a ketone as a substituent, right, that oxygen is kind of like a substituent now, then it's 3-oxohexanal. Okay, so let's do a couple examples here. So first of all, we're going to draw the structures corresponding to the following names. So the first one, 3-methylbutanal. All right. So first of all, the root is butane, right? So that means it's got 4 carbons in it. So let me just draw those. 1, 2, 3, 4. And I see here that it's an aldehyde, and that tells me that the carbon 1 is where the aldehyde functional group is. So this, we'll say that's carbon 1, that's carbon 2, that's carbon 3, that's carbon 4. So we'll say that right here on carbon 1 then is your aldehyde functional group. So it's got the C double bond O and then the hydrogen. Okay, connect all these. And then it's 3-methyl. So that means on carbon 3, we've got the methyl group. So CH3, that's a methyl group off of carbon 3. Okay, and then you can just fill in the hydrogens if you want. So hydrogen, oops, nope, that's not right. So hydrogen, and then forgive me for just being a little messy here, but and then this one is 3 hydrogens. Okay. Okay. It's a little nicer picture of it if you want. All right, so this one here, cis-3 tert-butyl cyclohexane carbaldehyde. All right, so you got to remember that when there's a ring involved, in this case we've got cyclohexane ring. Okay, so let's just go ahead and draw that cyclohexane ring. Okay, and whenever there's a ring involved and the aldehyde is a substituent off of that ring, it's just called carbaldehyde. So somewhere on this ring is a C double bond O with an H, that aldehyde functional group as a substituent on a ring, carbaldehyde. That's what that tells you. Now, it doesn't really matter where you put it on the ring because that identifies position 1. So that's like carbon 1, and then we just can count, whatever direction we want. Let's say this is 2, and this is 3, 4, 5, 6. And the reason why I did that is because now I've got to deal with this 3-tert-butyl functional group. So at the third position there is a tert-butyl functional group. But before I get too far into that, I'm also given this stereochemistry indicator. They're cis. So what does that mean? That means that the two sort of non-hydrogen functional groups are on the same face of this ring. So that tert-butyl group, okay, there's a couple ways I could draw it. I could either draw it like a T, where each one of these lines represents a methyl group, CH3 times 3. Okay, that's it. That's one way to do a tert-butyl group. Or a lot of times you'll just see it abbreviated as TBU. Okay, that's another I could have just written TBU right there to abbreviate the substituent. Okay, and it's cis, and then of course going into the screen, then we've got hydrogens on both of those positions. Okay, so this would be cis 3 tert butyl cyclohexane carbaldehyde. Okay, and again, here's a little prettier picture of it. All right, so now let's talk about some reactions that involve aldehydes and ketones. So first of all, one that we've already seen. Remember that in our material from last week, we talked about oxidizing alcohols, and you can oxidize a primary alcohol to an aldehyde and then to a carboxylic acid. And we said that if you want to stop at the aldehyde point, you have to do that with a special mild oxidizing agent called Des-Martin pyridine. Okay, well, this kind of takes it from there. Or, if you had just even started with a primary alcohol and a different oxidizing agent like chromium 2 oxide, okay, or probably chromium 6 oxide. All right, you start with the aldehyde, hexanal in this case, and you react it with this oxidizing agent in these conditions, and you get a carboxylic acid. So aldehydes oxidize to yield carboxylic acids, and this is just one oxidizing agent that happens to work really well, but there certainly are others. Okay, one other little detail we want to mention about oxidizing aldehydes is that it has an intermediate, because it's not really the aldehyde itself that's being oxidized. It's this intermediate that occurs in water. The water gets added to the aldehyde, and we're going to talk more about the mechanism of that later in this or maybe it's tomorrow, I forget which one. But you get what's called a hydrate, where a water molecule adds to the aldehyde, like a nucleophile, okay? And you get 2 alcohol groups, and then the oxidizing agent comes along and creates that double bond between the carbon and the oxygen to give you the overall carboxylic acid. Okay, so aldehyde oxidations occur through intermediate 1,1 diols or hydrates. Okay, so now we're going to talk about a type of reaction that involves aldehydes and ketones called nucleophilic addition reactions. Now, just remember that that's different than the addition reactions we talked about with alkenes, because those reactions were electrophilic additions. That's where, the substrate was acting as the nucleophile, and whatever was being added was the electrophile. Okay, in this case, it's just the opposite. The substrate is acting like the electrophile, and whatever's being added is acting like a nucleophile. So the nucleophile approaches, and it's, a little detail, but it's they know what it is. It's 75 degrees to that plane. Remember, with a carb, with this arrangement of atoms, they're all in the same plane because that carbon is sp2 hybridized. It's trigonal planar. Okay, so at 75 degrees to that plane, the nucleophile approaches, and then it adds to the electrophilic carbon. Okay, so that's what's going on here. So the nucleophile attacks the carbon. We know why, because that carbon has a partial positive charge on it. That due to the electronegativity difference between carbon and oxygen, that carbon is your electrophile. It's the partial positive charge. So the nucleophile adds to it. And then, as you can see, following the arrows, the electrons in that double bond move on to the oxygen to give you the formal negative charge in the oxygen. And then, we neutralize that negative charge by treating it with an acid, so it gets protonated and it becomes an alcohol. And now you've got the nucleophile added to that carbon. Okay, so it's an addition reaction because the nucleophile gets added to your substrate. Okay, so one little detail about, well, why is that so important? How do they know it's 75 degrees, or why is that important in detail? Well, it goes to the some molecular orbital theory. So I'll write a little bit. You guys don't have this in your handout, I know. So if you just want to kind of pay attention to what I'm saying, if you notice, this is a molecular orbital. Okay, kind of we're reviewing a molecular orbital theory a little bit. And so what's represented here is like the pi antibonding. Okay, that's the pi antibonding molecular orbital between the carbon and the oxygen. So this is your nucleophile right here, right? And the orbital that's got the electrons in it overlaps with that antibonding molecular orbital. Okay, and that just happens to be, both calculations and crystal structure show that bond angle that gets you the best overlap between your nucleophile and your pi antibonding orbital, that is, about a 75 degree angle. Okay. So that's why it is what it is. All right. So you don't have this list of nucleophiles in your handout, but it's something that should be familiar. We've talked about all these before, but recognize that nucleophiles can be either negatively charged or neutral. Nucleophiles can be negatively charged or neutral. So also remember that that doesn't mean that they're equally good at being a nucleophile. We learned before that nucleophiles are better if they're negatively charged. They're more nucleophilic if they're negatively charged, but nonetheless, even neutral molecules can behave as a nucleophile as long as it has that lone pair of electrons on it, like a water or an alcohol or ammonia or an amine. All of those potential nucleophiles have this in common. They've got that lone pair that's ready to behave like a Lewis base and donate that pair of electrons to an electrophile. Okay, so there's actually two general outcomes when you have these nucleophilic addition reactions. One of them is that you create this intermediate, like an oxygen that's got a negative charge on it, which gets protonated by water to produce, or an acid to produce an alcohol. So the product is a direct result of the intermediate being protonated by water or acid. Okay, but the second one is a new possible outcome, and we will see this in tomorrow's lesson, is that essentially the nucleophile can replace the carbonyl. So you started off as an aldehyde or a ketone, but you don't end up with an aldehyde or a ketone. It totally transforms into something different because the nucleophile forms that double bond, that carbon double bond nucleophile. Now, the nucleophile is usually a nitrogen-containing compound in that case, but and as I said, we'll get into that more detail tomorrow. But for now, just recognize that there's two possible outcomes of these nucleophilic addition reactions. You get an alcohol, which means you have the oxygen protonated by water or acid in a second step, or the carbonyl oxygen atom is protonated and then just eliminated to give a product with a carbon nucleophile double bond. Okay, so then we're talking about aldehydes and ketones, so let's distinguish them with these nucleophilic addition reactions. One distinguishing thing is that the aldehydes are more reactive than ketones in this type of reaction. Aldehydes are more reactive than ketones in nucleophilic addition reactions. Okay, so you can see down in your picture that's already on your screen and in your handout what's going on. On the left here in A, that's an aldehyde. You got the carbon with the hydrogen. In B, you've got a ketone because you've got the carbon and the carbonyl in the middle, and you got a methyl group on the left and a methyl group on the right, or a methyl group behind and a methyl group in front. So B is a ketone. A, actually, let me just write that down. A is the aldehyde. So this is showing you an aldehyde, and this one is showing you a ketone. Now, why? Why is it that aldehydes are more reactive in this type of reaction? Well, one of the reasons is because of steric hindrance, which we've talked about many times before up till now. So aldehydes only have one large substituent connected to the carbonyl, whereas ketones have two, and that shows up in these pictures. So with the aldehyde, you just got a hydrogen on one side. With the ketone, you got this big methyl group on the other side. So it's in the way. It's going to get in that nucleophile's way. Less so with the aldehyde because it's a smaller hydrogen. Okay? And the other thing that you could say is that the transition state for the addition is less crowded, okay, and lower in energy for an aldehyde than for a ketone. So the transition state for addition is less crowded and lower in energy for an aldehyde than for a ketone. Now, if you want, I didn't create any space right next to this picture on your handout, but somewhere, if you want to find some space, we can draw an energy diagram. Okay, so we put energy versus reaction progress. Okay, now remember which is what these typically look like. So we have our reactants. Let's say this is an exergonic reaction, so products would be down here. And so this would be, it goes up and we hit the peak, which is the transition state, and then it comes down to the energy of the products, okay? Well, that's just sort of a typical example, but what we're saying with these bullets here is that aldehydes looks a little bit differently. First of all, the aldehyde, it's less stable, okay, because it doesn't have as much of the alkyl groups donating electron density to it, so it's less stable. So for an aldehyde group, it's a little higher, start off with a little bit higher in energy, but also because there's less steric crowding, its transition state is lower. Okay, so for the blue would be an aldehyde, and then the red would be the curve for a ketone. Okay. Because there's less steric hindrance on the aldehyde, its transition state is actually lower in energy. So it doesn't have quite as big of a hump to get over. It's got a smaller hump to get over. Whereas with the ketone, you got a bigger activation energy to overcome. Okay, so this is something I already said, but let's just get it in our notes. The ketone actually has more, because it has more alkyl groups, stabilizes the carbonyl carbon inductively. This is something that we talked about with regard to carbocations. So that's kind of the reference, or the reference point in these first two pictures, that a secondary carbocation was more stable because there were these R groups, these carbon containing groups, sort of donating electron density inductively to balance out that positive charge in the carbon. But with an aldehyde, it's like a primary carbocation because you only have one alkyl group donating electron density to stabilize that positive charge. Well, that's what's going on with the partial positive charge. It's not a full positive charge like it is in a carbocation. It's a partial positive charge due to the electronegativity difference in the carbonyl, but it's still the same principle. With an aldehyde, you've got one alkyl group donating electrons to stabilize it, but with a ketone, you've got two alkyl groups donating electrons to stabilize it. So that means it's less reactive. Anything that's more stable is less reactive. So that's why aldehydes undergo this type of reaction, nucleophilic addition reactions, more readily than ketones do because they are less stabilized. Ketones are more stabilized. Okay, now a different type of aldehyde that does gain some stability are aromatic aldehydes. So aromatic aldehydes are less reactive in nucleophilic addition reactions. And again, that's because of delocalization. You have all these resonance forms to spread out that positive charge. It's not localized on one carbon. So it's smeared out over the whole molecule. So that stabilizes it and therefore would make it less reactive. Okay. So aromatic aldehydes are less reactive in nucleophilic addition reactions due to delocalization. Okay, so let's go through an example here of this is just another example of a nucleophilic addition reaction. So we'll do some curved, you see the curved arrows written here. Let's talk it through. So in this case, we have this cyano or cyanide ion, and it's going to behave as our nucleophile. So there's your nucleophile right there. And it's going to attack that carbon in the carbonyl because it's got the partial positive charge on it. Okay, so then what you form is it forms that bond. And then as we showed, the electrons moved from this double bond to the oxygen to give us that negative charge on the oxygen. But then in a second step, you come along and you add a hydrogen, an H plus, to that oxygen. This could be either from a water molecule or it could be from an acid. It doesn't really matter. But the point being is that you get an alcohol out of it. So we took it doesn't really matter what this is. This could be what's shown is acetone. This would be like a CH3 and a CH3. But if we just said that this was an aldehyde, then that it would be fundamentally the same reaction. But the point is, you did a nucleophilic addition to that carbonyl, and in this case, you ended up with an alcohol. And then the nucleophile that got added is right there, the cyanide part. One thing that just naturally happens whenever you have aldehydes or ketones in the presence of water is that they form what's called a hydrate. They react with the water. So aldehydes and ketones react with the water to yield what's called a 1,1-diol or geminal diol, or the more common term is actually hydrate. All right. So I will probably say that more often than 1,1-diol, just easier, right? But just recognize what's happening. It's kind of color coded. You see that you got the red and you got the blue. So this water molecule acted as a nucleophile. You got the two lone pairs on the oxygen. So it acted as a nucleophile. These electrons came up and went onto the oxygen, but then that oxygen snagged the other hydrogen from the water, and so you still have a balanced reaction here. Okay, so you got, the diol, the two alcohol groups. Okay, now the reaction is reversible. That's why we have the double arrows shown. Okay, and the position of the equilibrium, the side that's favored, it just depends on the structure of the carbonyl compound. In this case, it's highly favored to the left, the reactants, the acetone and water. But that's not always the case. It just depends on the aldehyde or ketone. The position of the equilibrium depends on the structure of the carbonyl compound. So let's just look at the mechanism here. So this reaction actually can be catalyzed either with an acid or a base. So we're going to kind of go through the mechanism of each way of catalyzing. So first of all, let's talk about how it's catalyzed in a basic solution. So we'll just talk it through. Both these diagrams are on your final page of the handout, so we'll just kind of talk through it. So remember, the characteristic ion when you have a basic solution, pH greater than 7, is a hydroxide ion. So this hydroxide ion behaves as the nucleophile and initiates things. It reacts with the carbonyl carbon, attacks it. So the electrons move out of the double bond and up onto the oxygen. Okay, so then you get the alkoxide intermediate, which then just snags the hydrogen from a nearby water molecule. Okay. All right, and then after that, essentially it results in a diol, a hydrate. Okay, and you get the hydroxide ion back because it took one from the water, and when you take away an H from H2O, what's left over is hydroxide, OH minus. Okay, so that's what it looks like when you use a base to catalyze this reaction. Okay, well, what about when you use an acid to catalyze this reaction? Okay, so hydration is also catalyzed in acidic solution. So once again, I'll just refer to the diagram on the back page there. So this one does the same thing, but it gets initiated differently. So in this case, the carbonyl oxygen behaves as a base. It's got lone pairs on it, so it can behave as a Bronsted base and accept NH+. But it takes a fairly strong acid to do that. So, you know, a hydronium ion from a strong acid like HCl or nitric acid or something, it donates an H+ to that carbonyl oxygen, giving it a formal positive charge. And so it doesn't like the formal positive charge on the oxygen, so it moves a pair of electrons up to the oxygen, okay? And then at the same time, another water molecule will attack as a nucleophile on the carbonyl carbon. All right, so then in step 2, you got the one alcohol because, you know, that's what happened up here. You produce this OH, okay? So here's that OH right there. And so now the water molecule is attached to, it was your nucleophile, so it is now attached to the carbon. And then another water molecule comes along and takes away one of its H pluses, right, to give you that second alcohol group. So you got a diol now. And then you, again, regenerate your catalyst. The catalyst doesn't get consumed in the reaction. So just like with the basic solution, we started with OH minus, we ended up with OH minus. With the acid catalyzed reaction, we start with H3O plus, we end up with H3O plus. Okay, so just, you know, understand the mechanism of how this hydration reaction is catalyzed by either a base or an acid.